Good morning, everybody. So it's my pleasure to be president of this defense of Sylvain LEDUR. I will be the president. I'm Frédéric Wirtz. I'm a senior researcher, and I'm doing my research at Grenoble University in the laboratory of electrical engineering. In this jury, we will have Irina Olejnikova, which is professor at the Norwegian University of Science and Technology. We have also Leven van de Velde, that is professor at Ghent University, and we will be the three rapporteurs of this defense. So we have written in detail the manuscript and have written the report about your work. We have in this jury also Pandelis Biskas, which is associated professor at the Aristotle University of Thessaloniki. We have also José María Yusta Loyo, that is associate professor at the University of Zaragoza. We have also Mr. Moulay Idriss El Alawi Faris, that is a doctor and that is working in the Air Liquide company. And we have the two persons that have supervised the work, Simon Kamal, which is chargé de recherche at Mines Paris PSL, and Georges Karionazakis, that is director de recherche at Mines PSL, Mines Paris PSL. So you have 45 minutes to present your work, and after the member of the jury will have a question with you about your work. So the floor is now to you, Mr. Sylvain LEDUR.
Thank you very much, Mr. President, for the introduction. Today I'm going to present my PhD thesis titled Optimisation of the Flexibility Potential of Industrial Electricity Demand. This PhD was conducted here at the Research Center per se in Sophia Antipolis, supervised by Georges Karionazakis and Simon Kamal. It's also a CIFRE thesis done at Air Liquide under the supervision of Moulay Idriss El Alawi Faris. I will start by introducing the context of this thesis and the objectives, then present the main contribution of this work, and conclude on the results and the perspectives. As you might all know, at any point in time, electricity supply must match the electricity demand. The supply and demand equilibrium is done through the various electricity markets. The electricity is delivered through the grid. And should an imbalance happen for one of the actors, ancillary services exist to restore the equilibrium of the system. This was historically done by conventional generation, as you can see here. But we can ask ourselves the question, what happens when we increase the share of renewable energy? By doing so, we increase the amount of imbalance occurrences, and we reduce the amount of conventional generation available for balancing services. To palliate that issue, one possibility is to shift part of the balancing responsibility toward the demand side. Here you have the example of an industrial actor providing reserve and an aggregation of residential actors doing the same. In this thesis, we will focus on the industrial part of this. From an industrial actor point of view, we can define the industrial flexibility as the modification of electric usage to reduce its costs, while helping the grid without negatively impacting its overall process. Here you have an example of an industrial process at Air Liquide called the cryogenic air separation that produces industrial gases for a various range of clients. For example, oxygen in hospitals. If we replace this by a more schematic view of the process, we can identify Air Liquide main goals when it comes to industrial flexibility. First, it is to ensure reliable supply to industrial consumer in a variable context. Second, it is to decarbonize the processes through direct renewable power consumption. And finally, the objective is to reduce its costs through optimal electricity purchase and the provision of ancillary services. We can link these main goals to identified challenges when it comes to the operation of our processes. First, there is a difficulty to identify and quantify the flexibility potential of complex industrial processes. There is also uncertainty regarding the ability to power industrial assets with variable renewable sources. And when trying to optimally purchase electricity, there is a financial exposure related to electricity markets. When we look at the state of the art, we observe that the existing literature mainly focuses on residential demand-side flexibility, which is smaller and needs to be aggregated. There is limited research on industrial flexibility, approximately 10 to 15 papers a year in the last 4 years, and before that, not so much. The few existing papers on industrial flexibility do not address the ensemble of challenges identified here, especially when it comes to the difficulty to identify the flexibility potential when we consider complex processes, and the realistic modeling of market participation. To answer these challenges, we have formulated 3 main objectives. The first one is regarding the complexity of the process and the flexibility potential identification. We want to develop a methodology to identify and quantify the flexibility potential of an industrial consumer. The second one is related to market participation and the uncertainty related to it. We want to formulate a decision-making strategy to valorize the flexibility of a plant in multiple markets. And the third one is a combination of the two when we have relatively inflexible assets that we want to, for which we want to valorize the flexibility. We want to investigate investments in new flexibility levers. Now, on to our first objective, which is flexibility potential quantification. The problem that we identify is that in complex processes, knowing the flexibility potential of each individual power component is not enough to characterize the flexibility potential of the whole process. Looking at the literature, when it comes to industrial flexibility quantification for industrial processes, the identification of the flexibility potential focuses on the limits of the feasible space of operation, but does not consider the possibility to move within this feasible space. Looking at power systems, on the other side, the identification of the flexibility potential this time considers the possibility to willingly move within this feasible space. However, the representation of industrial assets within this analysis are too simple. So to answer this methodology to identify and quantify, we have 3 main methodological steps. The first one is that we want to describe the feasible space of operation of a complex industrial process. The second one is that we want to quantify the ability to move within this feasible space. And finally, we want to identify the usual operating points of the plant when following a demand profile. But first, we can ask ourselves, what do we call a complex industrial process? Here is the picture from before. So we are still looking at the cryogenic air separation unit, which will produce gas that requires a certain chemical equilibrium within the process. This cryogenic distillation of air will turn air into its basic components, nitrogen, oxygen, and sometimes argon. If we look at a more schematic version of this process, we have at the center here the distillation process itself with different pressured column with different temperature where we will do the distillation itself. Looking at the flexibility aspect of these plants, we have our flexibility levers, which are power consuming components in the shape of compressors before and after the distillation columns and liquefiers. And we have as well liquid product storage. For this plant, we have product demand and clients. This product demand can take 2 shapes. It can be gaseous for oxygen and nitrogen, and it can be liquid for oxygen, nitrogen, and sometimes in specific cases, argon. The complexity sources for this kind of process is the chemical equilibrium within the distillation process that has to be preserved in the columns and the product output interdependency. Meaning that we cannot just change the power consumption of our compressors and other power consuming components. We also have to account for the distillation process itself. Now, if we look at the modeling of such an asset, here we have the representation of a mixed integer linear problem that we use to optimally schedule such a plant. So we use an objective function where we minimize on the top electricity costs and subject to a certain set of constraints that will describe the physical behavior of such a plant. So we have here the equations or a summary of the equations representing the distillation columns. Within it, we have mass conservation and process constraints, which are the origin of most of the process complexity. Then we have our constraint for power consuming components. Here I put an example of an equation for the compressor. In this case, they have a nominal power ramping here and the minimum and maximum flow Q within the compressor. We also then have liquid product storage constraints and the energy balance. Here is the tricky part. The mass conservation constraint will affect the process flexibility, therefore making the flexibility quantification non-trivial. Now, looking at our use case, we consider a very specific use case, a small air separation unit that will receive electricity from the grid, have two liquid product outputs, liquid oxygen and liquid nitrogen, with variable liquid product demand. And we have one gaseous output with constant gaseous product demand for the gaseous nitrogen. We have our flexibility levers, which are electricity consuming components, three compressors with a total of 4.5 megawatt theoretical total ramping, and a nominal power plant. The nominal power for the plant, which is 15 megawatt. It's the sum of the the compressors. Now going back to our methodology. Our first step of the methodology was to represent the feasible space of operation. To do that, we want to create a grid of operating points using the min-max output for both products. We will run a one-time step optimization in which we will fix the output values of the plant and check for feasibility. If it's feasible, we put it in the grid. If it's not feasible, then it doesn't appear in the grid. Here you have an example of the result found in the literature, where the authors do a fine representation of the edges of the feasible space, but we have limited information regarding what's happening inside the feasible space. Here is our first result for step one. We represent the feasible space, as we can see here on the right, with the white square being where we cannot go. And the optimal power bought by the plant for every operating point on the grid. We observe that the minimum and maximum outputs of the plant cannot be obtained for both products at the same time. From that, we go to step two, which is how do we find the ability to move within the feasible space of operation? To do that, we want to observe power ramping, which is the ability to change power from a given point. So to do that, we run a two-time step optimization this time to move from one given operating point within the feasible space to another within the feasible space, and we check for feasibility. If it's feasible, we check the power difference between the 2 points. We keep the move with the maximum power difference in each direction, and for each operating point, we have our maximum power ramping. We observe that it varies within the feasible space. And especially interesting, we have a limited upward ramping here when it comes to the lower value of liquid nitrogen production, which is a representation of the limits due to product output interdependency. Overall, we also identify a unilateral power ramping of up to 2 megawatts and never in both directions at the same time. So on the left, we have the downward ramp where we consume more electricity. We have higher possibility to go down in power, and the upward ramp, which is the opposite. From this, we want to identify which operating points appear or are used resulting from the scheduling optimization of the plants when we consider variable demand of the product. To do that, we run a weekly optimization to account for the product demand profile, and we extract the operating points from the results and their frequency of appearance. We obtain these results. Here on the plot, you see grayed out the unused operating points, and colored, you see the operating points that are used when optimally scheduling the plant with the frequency of appearance. Here in the table, you see the ramp available in terms of frequency occurrence. What we can see is that the operating points used are located at the extremities of the liquid oxygen here and here, output range, and that the liquid nitrogen on the y-axis product output is used to vary the power consumption of the plant. The 2 megawatt of ramp that we previously identified, only appear between 35 and 41% of the time, and never in a symmetrical fashion. Meaning that we cannot provide for one operating point 2 megawatt up and down at the same time. Now, to summarize the results for this first approach, We have identified and quantified the theoretical flexibility potential of an industrial plant, mainly starting from a theoretical flexibility potential of 4.5 megawatt from the individual electricity components. The methodology only identifies up to 2 megawatts of flexibility within the process due to the process complexity. Analyzing the practical flexibility potential available for ancillary services provision when considering demand profiles. Under usual operations, only a handful of possible operating points are used. The most efficient points are found on the extremes of the feasible space, which limits the available power ramp of the plant. Overall, this methodology provides a graphical information about the flexible potential of the process as a whole, instead of only considering the theoretical characteristic of each individual component. This work was presented in the PSCC conference in 2021 and then published in the Electric Power Systems Research Journal. Now on to our second objective for this thesis, which is the uncertainty-aware multi-market scheduling. Looking at multi-market participation for industrial assets, we observe that the literature lacks realistic simulations. Participation to market rules are not considered. For instance, gate closure are not considered. Prices are assumed to be known in advance. The granularity of the bids are not considered. And this whole can have a large impact on the financial result of the plant. To analyze that, we have a methodology in 2 points. First, we want to simulate the day-to-day operation of a flexible asset on electricity markets and secondary reserve mechanism. And we want to manage the uncertainty coming from the renewable power and the sequential electricity markets. Looking at the electricity purchase and reserve provision side. Electricity markets span on different time scales, which allow us to hedge the uncertainty related to these markets. When we look at direct renewable power consumption, we cannot buy it on the short-term markets because they do not allow for the identification of the source of the electricity that we receive. To have certainty and certify that the electricity we receive is renewable, we go through PPA contract, which are long-term contract called power purchase agreement, which allow for the direct purchase of renewable power for a certain price that is set while the contracting, but we will go back to that a bit later. Then we have the reserve aspect and the balancing aspect of the markets in green, where we will have market operator receiving bid to balance the market, to balance the grid through several markets. The volumes offered by industrial actors are of high interest to the grid operators because of their large power and energy density compared to residential flexibility, for instance. The market participant is first remunerated through capacity reserve in a day-ahead fashion, before being remunerated for the effective energy used when considering the effective need of balancing of the system, this time with intraday bidding. Most reserve markets allow asymmetrical reserve participation, which is good for us, as we have identified in the previous part that we could not provide as much reserve as we wanted in a symmetrical fashion. To simulate the decision-making of the plant as the day goes by, we developed a rolling horizon algorithm that we have represented here. An optimal scheduling of the plant will be run every 15 minutes with evolving forecast as inputs here on the left and optimal market bid as outputs on the right. Below we have the time scale of the markets. When no gate closure is reached, the position on each market is free and the optimization problem can feel free to optimally dispatch the power bid. When the rolling horizon reaches gate closure, the last optimal position returned by this optimization problem are used to compute the market clearing. So we decide by the status of the markets if we are scheduled, if we are accepted, to what price, to what volume. And then the market clearing results are used as input this time on the left for the optimization. And we go through that throughout the day and throughout the year. Now looking at the optimal scheduling itself. So we represent it using an optimization problem, which is a mixed integer linear programming once again. Here we present the objective function and the parameter. The main objective is to minimize electricity costs and maximize reserve revenues and product output revenue. For the electricity costs, we will have the power bought on the different markets that will be considered a variable, multiplied by the price of the market, which is an uncertain parameter. The energy received through the PPA or for renewable power is considered an uncertain parameter because we have the assumption that we have to consume anything sent by the wind power plant. When it comes to reserve revenue, the work is a bit similar. We will multiply the power reserved by the capacity reserve bids. So the power reserve is a variable and the capacity reserve bid is as well an uncertain quantity, an uncertain parameter. And the same is done for the energy activated through the reserve. For our uncertain quantities, we consider point forecasts. Looking at the plant operational constraints, we have here expressed the power market quantities, the day ahead and intraday, as PM. And we have two types of constraint presented here. First, the minimum and maximum power consumption of the plant, and the minimum, the maximum up and down ramp authorized by the plant. Because we do not know the amount of energy effectively activated for the reserve, because it depends on the current status of the market, of the grid, sorry, in terms of balance, we cannot use the reserve provision to keep the power balance of the plant. Meaning that for the min and max power, only the reserve direction that will adversely affect the min-max constraint is considered. For instance, here, this one will only threaten to violate the constraint, whereas if we put this one, we would help the system keep in balance. The same logic is applied to the power ramping. The plant power ramping constraint must consider the change in reserve direction from one time step to the next, and only in the direction that will adversely affect the constraint. We have to note that we are using generator point of view, meaning that upward reserve implies a reduction of the consumption of the plant. Looking at market rules, we only enable one direction per time step for the participation on a given market when we have bidirectional markets, so reserve and intraday market. To do that, we introduce a binary variable, which is used to manage the direction of the participation. To manage the locked participation due to the rolling horizon and the reaching of gate closure, we introduce these constraints, where the power for a given market is set to be equal to a certain position, only when this theta GCT is equal to 1. Meaning that when the rolling horizon sends the identifier saying, we reach the gate closure, you cannot change your position on this market anymore. Now onto the uncertainty management. The first goal that we have as an industrial consumer is to reduce our imbalances. So we want to focus specifically on the wind power, which is uncertain and that will cause imbalance. To do that, we decided to go for a robust reformulation of the problem. And here we explain how we did that. Before, we had a point forecast for the PPA here. We now have a box uncertainty set, meaning that our power shift from the PPA will be comprised between these two minimum and maximum values. The objective of the robust optimization is to find the optimal solution against the worst case realization of the uncertain parameters. Here we have our previous maximum power consumed by the plant constraints. And we have our robust reformulation of this constraint, where essentially what we do is that we put an optimization problem within the constraint, which cannot be solved as it is, so we have to simplify it. Because we only have one uncertain parameter for these constraints, we can reformulate it because actually the result of the optimization problem, the maximization here, is quite straightforward. It's the maximum value of that the PPA can take. We can do that for every constraint containing the PPA parameter, and we end up with the robust reformulation. Now, onto our use case. For this part of the work, we decided to consider electrolysis and green hydrogen production. The goal of this study is to reduce the cost of production of green hydrogen, which is very high due to electricity prices, through reserve provision. We will receive our wind power through the PPA contract that we mentioned before. And this PPA contract, in terms of price, is indexed at 80% of the day-ahead market price and capped to predefined limit to protect both the producer of the electricity and the consumer of the electricity, us. We have to consume everything that they send, and we have uncertainty on the production of the wind power, which is why we have a premium on the price, and we buy it at 80% of the day-ahead market price. Hydrogen produced through power received from the PPA will be considered green. Any hydrogen produced from any other source of electricity coming from the grid will be considered gray. We consider for the reserve market secondary reserve because this is what is more appropriate for our response time and degradation of the electrolyzer. The green hydrogen is sold at a premium, here €6 per kilogram, whereas gray hydrogen is sold at €2 per kilogram, which is roughly the price that we sell hydrogen at when we use fossil fuel-based technology. So the ultimate goal would be to reach €2 per kilogram for the green hydrogen. The hydrogen produced by the plant is sent to a hydrogen network. Therefore, no specific demand is to be satisfied. Looking at the market participation, we want to simulate the run over the year 2021, which is interesting because on the second half of 2021, there was an energy crisis due to a flare of natural gas prices. This simulation will therefore illustrate the behavior of our algorithm in extreme prices situation. We also consider German market rules and prices because of the availability of the reserve prices and quantities to the public, and because they have similar rules to the ongoing European reserve market harmonization. On the side of wind power profile, we obtained it from the Belgian offshore platform. Once again, because historical production data was available, and because its geographical location is close to Germany, and therefore we can capture the effect of high wind power penetration on the market prices. Now, onto the results. Here we will present an illustrative run that was done during year 2021, where we have the power market transaction for the electrolyzer, for the day ahead in blue, intraday market in pink, and the PPA direct consumption in green. We observe that the electricity is bought on the day ahead market to produce gray hydrogen when the power prices are sufficiently low to reach the €2 per kilogram of prices, and the plant consumes all the power received from the PPA contract. Looking at the reserve, we observe that the plant provides reserve around its power profile. Here we can see it. And if we look only at the reserve, we have it here at the bottom left. We observe that to be realistic compared to the literature, the effective energy activation of the capacity reserve bid is dependent on the real-time imbalance of the system, meaning that for every time step, the effective energy activation of the reserve will vary, and it's something that we cannot predict. Now, looking at more higher view results for the year, we average the cash flow increase between no reserve and with reserve on top over here over the year. And we do something similar in the bottom with imbalances, without reserve on the left, with reserve on the right, with percentage of occurrences, and the 95% CVAR on the volumes of imbalance. What we observe when we look at the cash flow, we observe that reserve provision generally increases the cash flow. We have the average over the whole year on the right. The reserve addition is particularly advantageous in times of crisis, which was the second half of the year, where we observe up to 300% of increase in cash flow during the crisis due to very high electricity prices. When we look at the imbalances, we observe that the robust approach reduced the occurrence of imbalance quite drastically, here without reserve and here with reserve. We also observe that the reserve provision further reduces the imbalance. Now onto our final result, which is the green H2 break-even price. What we call green H2 break-even price is the price at which we could sell the green H2 if we used all the additional profit to reduce the sell price of this hydrogen. We observed that we have better performance from the robust approach before the crisis here. However, the reserve provision with the robust approach is not enough to compensate for the adverse effect of the crisis here because of its more conservative approach. Now to summarize the result of this part. The behavior of an electrolyzer providing reserve services was simulated. We observed that adding secondary reserve increases the average cash flow, and that this can bring down the selling price closer to gray hydrogen. So if you remember, it was around 4 and 5 euro per kilogram. So it's not yet around the 2 euro per kilogram, which is our goal. The impact of uncertainty was assessed. We observed that the deterministic and robust approach have similar cash flow performance. However, the robust approach shows a great imbalance improvement. We also observe large differences between the perfect knowledge and the uncertain approach, hinting at the fact that we could increase the performance of our algorithm by increasing the quality of the forecast, especially when it comes to reserve market prices. Now on to the last part of our presentation, the third goal, which is the investment in additional flexibility level. The problem we have is that the inflexible aspect of air separation unit prohibits them from operating with large amount of renewable energy. In the literature, we have observed that the provision of ancillary services for this type of plant is only considered through the addition of an external flexibility lever. And to our knowledge, the case of an air separation unit fed directly by renewable power production is not widely addressed in the literature, which is why we will use it as a use case for our investment in flexibility lever approach. Our methodology will be to first assess the viability of an inflexible asset, in this case an air separation unit, in a certain markets and power conditions. And then we will investigate the investment in additional battery storage as a new flexibility lever to further decarbonize the process. Here is our use case. The general goal of the study is to assess the ability of an air separation unit to operate under uncertain conditions. So we take our previous air separation unit and we input it in our market participation framework. So we still have the same context around the market participation with variable renewable power received from a PPA contract indexed at 80% of the day-ahead market price. We can buy electricity from the grid for the bulk of the electricity consumption. And we have to satisfy the variable demand of the plant and the two liquid product and the gas demand that is constant. Here we have a reminder of our two methodology. First, we want to analyze the reserve provision of the reserve provision analysis for the plant. So we have different market setups where we will observe the effect of uncertainty on such an inflexible plant. And then we want to add a battery to increase the amount of renewable power that we can receive. Because we only consider the amount of renewable power that we can receive, you note that we do not provide reserve anymore for this step 2. We only focus on the wind power itself. The rolling horizon is run over 3 different weeks of year 2021 because adding the air separation unit within the optimization framework makes it harder to compute, and therefore we had to average over 3 weeks and extrapolate what would happen over a year. Now onto the result analysis for this simulation. Here we have the average electricity costs of the average electricity cost for the plant for various amounts of reserve provided on the x-axis, and below the imbalance occurrences and the imbalance average volume with the 95% CVAR again for once again various amount of reserve produced. And the various color are our various strategy depending on the market participation and the uncertainty. We observe that without any wind power, the reserve provision presents an economical interest up to 2 megawatts. When we start providing 3 megawatts, the optimization problem cannot effectively manage the fact that our plant cannot go up more than 2 megawatts, and therefore we have an increase in cost and an increase in imbalance. Which is also the second point. Imbalance never occur, or very rarely, up to 2 megawatts of reserve, but more frequently at 3 megawatts. This is in line with what we find in the first part of the work, where we identified up to 2 megawatts of reserve for a plant, and not 3. When we add wind power, and intraday markets. We observe that this overall reduces electricity costs because we have electricity that is less expensive, and we can additionally reduce the cost on the intraday market. However, intraday market addition increases the amount of imbalance, which we can see when we compare with and without intraday on the plot. The deterministic approach presents a higher cost reduction, which we see here with the red square. However, we drastically increase the imbalances. We see that for no reserve, we are up to 27% imbalance, which is enormous. The robust approach, however, reduces the imbalance appearances, and the addition of reserve further reduce the imbalance, as we saw before in the objective 2. However, what we can observe is that air separation unit has difficulty handling variable renewable power on its own. To help with that, we will consider the addition of a battery. Here you have the optimization constraint for the battery. So we have the market constraints, the storage for the battery constraints, the direction we only allow charge or discharge every time step with the binary variable, and we have introduced a cycling constraints on the energy usable by the battery over the day. Because the optimization do not see what happened before in the day, we have to handle it in the rolling horizon algorithm, and therefore which is why we input here this quantity of energy, which is the remaining energy for the day, to the battery, considering what we used before, obtained from the rolling horizon. We observe that doing so without any restriction on the usage of the battery will operate on the markets to catch the spread of prices between the markets, generate a profit, but do not have electricity enough to actually balance the plants, which was why we added it in the first place. This is why we introduced this restricted battery management strategy, where the optimization problem cannot plan battery usage more than 6 hours ahead, which is the same as the intraday market participation. Therefore, it can only be used as a balancing tool without any day-ahead market bids. One specific point, the results are presented through a sensitivity analysis, and we consider only a 2-hour battery system, meaning that our batteries are dimensioned so that they can charge fully or discharge fully in 2 hours, which is why all the quantity for the batteries will be expressed in megawatt hour without explaining the power output, the maximum power output of the battery. Looking at the results. Here we have the average cost reduction when we oppose it to a no battery case for various with power nominal size. And below we have the imbalance occurrences with the same setup. And the colors are the different battery size. We observe that adding a battery always reduces the costs. Note that we do not consider the investment aspect at this stage. Without intraday market participation and without any restriction on the participation of the battery brings large electricity cost reduction, but do not improve the imbalance management. In some cases, it even worsens it. Adding restriction, we effectively reduce the imbalances, but we drastically reduce the cost reduction. To palliate that, we decided to add the intraday. If you remember before, the intraday was worsening the situation in terms of imbalance. We decided to combine it with the battery addition with the hope that the battery would reduce the imbalance and the intraday would increase the cost reduction, which is what happened. We can see here that for the average cost reduction, it is higher when we add the intraday, and we keep our imbalance reduction. Now on to the investment aspect. The objective is to make the project of investing in a battery viable. To do that, we have to know two things: the capex of the battery, which is the investment price, the cost of the battery itself, and the expected cash flow of the battery, how much money we will generate with it to refund the battery. The thing is that in the literature, the capex for such kind of battery varies quite a lot depending on the source that we look at. Which is why we decided to not include it in our computations. We observed, however, that it rarely goes below 400 euro per kilowatt hour. What we did is that we considered a metric called discounted cash flow, where we take all the expected revenues over the lifetime of the battery, and we account for the future value of money, meaning that future cash flow will have a lesser value in 5 years than now. How we can interpret this discounted cash flow is note that we also normalize it by the battery size, which is why it is expressed in euro per kilowatt hour of battery. This discounted cash flow can be interpreted as the maximum capex that we can afford to invest in a battery if we want to have a viable project. When we look at the DCF for the restricted and the restricted intraday with intraday management of the battery, we can observe that the intraday market participation is likely to be necessary for the investment to be viable. When we don't have any intraday, we observe that all the discounted cash flows are, most of them, except one, are lower than 400 euro per kilowatt hour. When we look at this discounted cash flow only, the best investment is always the smaller battery. However, if we want to combine it with the cases where we have imbalance occurrences that are lower than 2% of imbalance, we obtain this table. We have varied the discount rate when it comes to investment. It depends on the amount of debt that you put into your investment, so it gives a broader view. We observe that we only have 6 scenarios that have imbalance occurrence lower than 2, the best one being 5 megawatt PPA with a 2 megawatt hour battery. That brings us, if we keep the 8% that we had on the plot, 700 euro per kilowatt hour for the discounted cash flow. We also observe that only one scenario reaches lower than 1% imbalances, which is the lower amount of of wind power with the higher sized battery at the DCF of 547 euro per kilowatt hour. Now, to conclude on this part, the viability of an air separation unit in a certain market and power condition was assessed. We observed that the air separation unit has limitation in terms of reserve provision, which are consistent with the result obtained in the flexibility quantification approach. The air separation unit cannot handle variable wind power on its own. When we look at potential investment in additional battery storage, the battery needs restrictions on decision lead time to effectively be used as a balancing tool. The intraday market participation is made viable by the addition of the battery. And we have 6 scenarios that show less than 2% imbalance occurrences, but only 1 that show less than 1%. Now to conclude on the result obtained in this thesis, the contribution and the perspective. Regarding the flexibility identification and quantification methodology, we propose the methodology to simply and graphically represent the flexibility potential of a complex industrial process, accounting for this process as a whole. The effect of process complexity within an air separation units on process flexibility were observed. These results were presented in a conference, the PSCC 2022. So we sent it in 2021 at the conference 2022. And published it in the journal Electric Power Systems Research. Regarding power flexibility valorization through multi-market participation, we developed a rolling horizon algorithm to simulate the realistic operation under uncertainty of industrial assets, providing reserve with renewable power sourcing. In electrolysis application, we observed that reserve provision can bring a significant decrease in green hydrogen production cost of 8.5 roughly %, but does not yet compete with its carbon-based equivalent. This electrolysis study will be sent for review in a journal paper under the title Optimal Scheduling of a Large-Scale Electrolyzer for Grid Services Provision and Renewable Source Hydrogen Production. When looking at air separation unit applications, the plant cannot manage uncertain renewable power on their own. However, if we add a battery storage, we can make it viable to invest in with the proper market participation and battery management strategies. Now, looking at the perspective for this work. Once again, going back to flexibility quantification, we could extend the flexibility quantification methodology to consider plant design with flexible operation in mind. Taking a greenfield approach. When we design the plant, we want to plan how we could use it flexibly and therefore have more freedom when we design this plant. We also could explore the impact of more complex modeling on the flexibility studies that we performed in this thesis. Regarding flexibility valorization, we could decide to go toward industrial clustering, which could increase the amount of flexibility available to industrial actors. Combining different plants with various amount of flexibility could, on the global scale, increase the flexibility potential. We could also look at storage management outside of the limited optimization time frame, which actually that needs to be investigated. On this particular point, we have optimized storage over an optimization time frame, which was a few days. When we have storage that are designed to operate for demand with weekly profiles, the optimization cannot see the future time step, the previous time step. So we have to find a way to optimize the storage management outside of this optimization time frame. It clashes, however, with the concept of rolling horizon, which requires an optimization with limited time frame. A similar problem happens with flexibility lever investments, where we want to optimize the investment in additional flexibility lever instead of using a sensitivity analysis. However, to do that, we need longer simulation timescale and optimization timescale, which are not compatible with the rolling horizon approach that we used. Thank you very much for your attention.
Mr. LEDUR, the declaration was shorter than the defense. Thanks. So that's why I am happy to give you the feedback that the jury was unanimous to say that the presentation was very predictable, very dynamic, clear and stable. Slides were well organized, very complementary to the ministry. The jury also underlined the importance of the topic addressed, industrial valorization, importance addressed for the share of renewable energy, what is important for energy transition. You also address the important topic of industrial modeling of flexibility, for which there is a lack and a need of academic studies. And we underlined also the importance of the work you do for addressing the cooperation between academic and industry. And we also thank you for the contribution to the active participation of demand into the electrical market. Thanks. During the presentation, you also demonstrate the full knowledge of the specific topics you addressed. The method and concept were well explained, with a proposition of optimization models and methods that have been validated with data coming from real industrial field and use cases. This was appreciated. You demonstrate by this way a very good knowledge of the state of art, as well as good analytical skills that were demonstrated with the answer you bring to the very numerous and accurate question of the jury. And your answers also underlined the novelties and the very interesting and original results you produced. For all those reasons, the jury unanimously decided to award Mr. Sylvain LEDUR the grade of Doctor in Energy and Processes of Paris Science and Letters University, and I congratulate you.